G'day everyone and welcome back. In this video, we're going to be looking at how structural fire behaviour has changed significantly over the last few decades and what those changes mean for firefighters on the fireground. Because since the 1960s and 70s, we've seen the time to flashover reduce from 30 minutes down to times as low as 4 or 5 minutes. And we've also seen that structural collapse is happening at a much earlier stage than has ever happened before. And we're also seeing extreme fire events such as ventilation-induced flashover, backdraft, and smoke explosions far more often than we had previously. So the question is what has actually changed? And the answer is, well, quite a lot. Because when we have a look at modern homes in comparison to homes from the 1940s and 50s, we can see that there are a lot more synthetic and man-made materials being used to furnish these homes. And we can also see that the building materials themselves have also changed. Where once upon a time we were using a lot of hardwood and more dense products to build our home, whereas today we're using a lot more lightweight construction like pine and LVLs, and the connection methods have also changed because once upon a time the connection points between timbers was protected deep within the timber in the form of large nails, whereas now many connection points are on the external of these timbers in gang nails and similar types of connection methods. And these aren't the only changes, because we're also changing the floor plans of our building where we're moving to more open plan style living. Now this means that as a fire is growing, it's going to have access to more oxygen, which means the fire is able to progress at a faster rate than it may have otherwise done so. So we're going to go ahead and dive into each of these factors to see just what effect that they've had on the modern fireground. And we're going to start with fuel. Because once upon a time, the fuels that we filled our homes and businesses with were largely naturally based materials of cotton, wood, and wool. Now, while these materials are undoubtedly flammable, they are nowhere near as flammable as the modern synthetic materials that we are putting inside our buildings, such as polyurethane foams that make up much of the padding inside modern furniture. And when we look at modern synthetic materials, we can see that their heat of combustion, which is how much energy they're releasing on a pound-for-pound basis with other fuels, is much higher than older legacy materials listed here as cellulose, which is one of the main building blocks for wood. And so when we have a look at something like polyurethane, we can see that there's far more energy being stored inside these fuels that are available for the fire to burn. Now this means that when we burn a polyurethane in comparison to wood, we're actually getting more energy being released by that fire. And that's not the only component that makes these fuels more flammable, because quite often these materials are often much lighter and have a much lower thermal inertia. Now this means that it takes less energy for these fuels to be heated up and begin to pyrolyze than it does for the more dense and higher thermal inertia fuels like timber. So when we're looking at modern synthetic fuels, we can now see that not only do they release more energy on a pound-for-pound basis, but they can also take less energy to increase their temperature to the point of pyrolyzing, which means they can then begin to start to emit more and more flammable smoke. And this means that the whole system works in a big feedback loop, where we see that less energy is needed to go into the system to then release more fuel, which then creates more heat, which then goes back into the system, and the whole thing can begin to snowball, meaning the fire is able to burn much faster than it would have before. And this is clearly visible here in a comparison between some polyurethane foam and a piece of timber, where the piece of timber takes a lot more energy to be ignited than the polyurethane foam, which as soon as it is ignited, it burns easily and quickly. And the effect of this was clearly demonstrated by Underwriter Laboratories when they did the side-by-side comparison of modern versus legacy fuels, where the room with the modern fuel load progressed to and through flashover in less than 5 minutes. whereas the legacy fuels took as long as 30 minutes to reach flashover. And this is just a very clear example of the effect of modern synthetic fuels and how they have dramatically changed the modern fireground. Now, this is where things have really changed, because as you've just seen, fires burning in natural materials can still progress through flashover, but they can take a lot more time to get there. Whereas fires burning in more modern fuels can release a lot more energy a lot faster than the legacy style fuels, and therefore reach flashover in much shorter time frames. But to be able to release all of this energy, these fires will need access to an air supply that is sufficient to allow all of those flammable pyrolysis products to be fully oxidized. And in the case of a polyurethane foam, which is a hydrocarbon, there are many different chemicals that can be emitted, but the main byproducts from a well-ventilated fire will be H2O, which is water, from the hydrogen, and carbon dioxide from the carbon, with carbon monoxide making up a smaller proportion of the smoke. Whereas, if the fire starts to use more oxygen than what is available to it, it will begin to become underventilated or ventilation controlled. When this occurs, there will be less carbon being fully oxidized, and as a result, more carbon monoxide and carbon will be released from the fire. Now, what this means on the fireground is that the fire will begin to produce more smoke, and that smoke will not only begin to further restrict the inward flow of air, but the smoke itself will be becoming more flammable and more toxic. Now, what this demonstrates to us is that while every fire is different and needs to be treated that way, it is also quite possible, if not likely, that the fire will have reached some kind of ventilation control by the time a fire brigade arrives, and that any addition of air without effective suppression to the fire will most likely result in a rise in the fire's heat release rate and an escalation in the fire. Now, there really is a lot more to the subject of fuel control and ventilation control, but in the interest of not going down a massive rabbit hole, I'll save that for a video of its very own. Now, as I've already mentioned, this isn't the only factor that's changed in modern buildings, because the actual floor plan of these buildings has also significantly changed. Whereas back in the early 1930s, 40s and 50s, it was more likely to have smaller rooms and more compartmentation within a building. Whereas today, it's more likely for us to have a more open plan living space, which contains a lot more oxygen, allowing the fire to burn and create more heat and therefore access a lot more fuel before its growth is finally restricted by the limitation of the available air. Now, this brings us to the third factor that has really changed how these fires are going to burn, because once upon a time there were a lot of hardwoods and large thick timbers being used to construct these buildings, whereas today we've moved to a lot more engineered timbers such as chipboard and other pine and resin-based materials. Now, while these materials are excellent for building materials because they are lightweight, easy to manufacture and easy to use, they are also a real problem for firefighters because their lightweight nature makes them faster to burn and quicker to collapse than older, more legacy-style materials. Now, this means that the time to structural collapse has also reduced significantly in more modern buildings, as we've seen a move to these lightweight engineered timbers. So all of this just goes to show that modern fires can be significantly different to fires that we may have encountered in the decades past, with shorter times to flashover, more flammable and more toxic smoke, and a greater likelihood of structural collapse. And so the more that we can learn about structural collapse and how fire behaviour has changed, the better off we're going to be. But that's it for this one. Thanks very much for watching. If you liked it or have a comment to share, chuck it down below. Give the video a like or a share, or I don't know, do the followy things, all those YouTubey things. I'm not very good at that stuff, but you know what it is. You know how to do it. Thanks very much. Catch you in the next one. Bye. So all of this just goes to show that modern fires can be significant. So all of this just goes to show that modern fires can be significant. What's going on?